Okay, everyone, this is the big one in this section, allocation methods. So what I want to talk about here is I want to first define the problem. What are we trying to solve with these methods, with these algorithms? I want to talk about continuous allocation, linked allocation, and indexed allocation. So the problem at hand is, how do we allocate space to the files in the actual secondary storage? The main constraints that we face is efficiency and speed, right? We want to efficiently map things in there so that it's very space efficient, but we also want to be able to retrieve files very quickly. In contiguous allocation, this requires each file to be stored in contiguous blocks. So for instance here, this file named count starts at block 0 and is length 2, so we know that it encompasses 0 and 2, the 0 and 2 block. Whereas F starts at 6 and is 2 in length, so we know that that's 6 and 7, so on and so forth. Super easy to implement. Very little head movement on HDDs, that's very minimal, which is nice, because basically all it needs to do is it needs to get to the starting location, and then you can assume from there that they're all going to be in the next block until the end of the length, of course. Some cons, so finding space. So if you remember from our contiguous memory allocation, we had some issues there, right? So finding space was a challenge. We had a lot of external fragmentation where we had space, but it was so fragmented that we couldn't actually fit any of the new requests coming in. And so we have the same issue here. And also the file growth is limited. So let's look at one of these for an example. So if for instance, what starts at 14? TR wanted to increase itself by 3, wanted to move to 6, couldn't, right? Because at 19, something's already taking up that spot, and so we kind of limit our file growth. So I want to look at each one of these cons and talk about how we can mitigate them. So finding space. So again, this is a similar problem to what we face with contiguous memory allocation. We could use the best fit, the first fit. So best fit is a little bit more efficient, although it's not significantly more. When it's been tried in larger systems, it's found to not be that much more efficient. Or we could do first fit. Now first fit's a lot faster, right? Because as soon as it finds a chunk that it can fit into, it's going to just fit there. So we can use those similar algorithms that we've already used before. External fragmentation, so these holes that are created that are not able to fit new files, we can use compaction to actually compact them down so that we can use those holes, so they become bigger holes that we can actually fit files into. So you can do this in two ways. The first way that you can do it is you can literally copy everything over to everything that's being used, all the files over to another part of your storage, and then rewrite it into the main storage place. This usually requires downtime, so your system actually has to be down for this to work. So that's a trade-off. You can also do this on the fly, but your computer will be incredibly slow. It'll be up. You can use it, but it's going to be really slow because it's going to be trying to compact things. It's going to try to wait its turn to find files that aren't being used. It's going to try to compact that and then move things around before you actually notice, and it's just going to make your computer very slow. File growth limited, so okay, next block might already be taken, fine. So what we can do is we can issue a user error to the user and say we couldn't do it this time, maybe try again, or choose a different spot to save it in, or we can copy it to a larger hole. So we can take TR here that we wanted to give it 6, and we could actually copy it into maybe this hole. So it would be here, and then it could actually take up its extra 6. So we can do that. Most OSs don't use this scheme. The cons much outweigh the benefits, even though it's super easy to implement. In practice, it does not work very well. So moving on to linked allocation. So each file is a linked list of blocks, and this can be scattered. So the pros here, there's no file limit, right? So if I have of course, unless of course you run out of your storage completely, there's no file limit. I can always add another block onto the end if it's free. No external fragmentation because blocks can be taken from anywhere. It's not like we have holes that we need to try to fit files into. And so this makes it generally easier to find space. Cons. So this linked allocation, it's a linked list, so it relies on pointers. Pointers take up space. There's also no random access, and because we're using a linked list, the reliability is not as great. So pointers. So why do they take up space? Because they are pointers. They take up space. So within this block, you're going to have some area that you can actually use to store your file, but then you're also going to have to save some space for pointers. So this can cause a lot of overhead and cause it to be inefficient. One possible solution to this is clustering. So what you can do instead of just having one block in each one of these linked systems, you can cluster them such that you have, so maybe you cluster them into 4s. And then when you have a file, you simply link the clusters. All right, so some issues here. Internal fragmentation now, right? So if you have a small file that only would have needed one block, but you're assigning a whole cluster to it, so you're going to have some internal fragmentation. I/O performance, right? So when you want to actually pull data from the store, they're clustered, so you have to pull the whole cluster. And so even when you ask for a very small amount of data, you're going to get a larger setback than you need, possibly. Random access. It's a linked list, so it's going to be slower. It's going to require more head movement as well, right? Because you're moving from way different parts possibly of your storage. And reliability. What if one of these links gets corrupted? Possible solutions here. So you could use a doubly linked list and add another file to record relative locations. So you would have kind of a backup. So you would know how things are connected. But again, all of this causes some overhead. Oops, there's an arrow down there. Overhead. Okay. There's still really no solution to direct access. You don't have direct access. FAT is a variation of the linked allocation, which actually does allow for direct access. So what happens here is that there's a FAT table that for each volume, and preferably this is stored in memory, so on memory, and it has one entry for every block. And so your directory entry, so your file name, will have a start block, and then it will have the start block will have a pointer to the next block and the next block and the next block. So now instead of having to walk through your actual storage here to walk through all of these, you're doing this in memory, and so you can kind of skip around that way, and you can actually, if you need to directly access something with an offset of whatever in your file, then you can actually calculate that based on the entries in the table, and you can just directly index right into it. Okay, so an example question that might show up on a test. Hint, hint. So assume that we have a file test and it's allocated in blocks in the following order: 2, 6, 3, 8, 4, 5, 1, and 7. So I may ask you to show the block orientation assuming linked allocation. Okay, so the first thing that I would want you to show me is to say, okay, file. So remember, we have our linked allocation here. We have a start and an end that's in the directory. So the first thing I'd want you to tell me is the start and the end. So the start is at 2, the end is at 7. Okay, so that's the first thing I'd want you to give me. And then from there, it's pretty straightforward. So we have 8 slots, so I'm going to go ahead and mark those. I don't know. I guess I'm going to end up with 9. I'll just do that. So this would be 1, 2, 3, 4, 5, 6, 7, 8. And now, so we start at 2. It's going to point to 6. That's the next part of the... Here, we'll do different colors. So we go to 6. From 6, we'll go to 3, 3 to 8, 8 to 4, 4 to 5, 5. Dang it. Why did you guys not tell me that? All right, back up, back up. Oh, not that far. I started at 1. Let's redo this. Okay. 2 rather. So we start at 2, we go to 6. From 6, we go to 3. From 3, we go to 8. From 8, we go to 4. From 4, we go to 5. From 5, we go to 1. And from 1, we go to 7. Okay? So that's what I would be looking for if I asked something like this. So this would be assuming linked allocation. So indexed allocation. So basically the idea here is that we want to move all those pointers that we had that were taking up space in the blocks to one location, and we call this location the index block. So there's going to be one block in here whose only job is to keep track of whatever other blocks this file is stored in. So some pros, no internal fragmentation. Again, we have direct access, which is nice, right? We have a list of everywhere, all of our file. And we have no file limit, right? We can add more and more entries to this index file as we see fit. The only limitation that we will find, but I'll talk about how we can mitigate this, is if we overrun the amount of entries that we can actually hold in each block. But we'll talk about how to fix that. Some cons. So design of the index block. We want to minimize this, but still allow large files. And the reason we want to minimize it is because it takes up space, and it takes up a block that we could have used for other storage. So we want to make sure that we make it as small as possible such that most of the files can be just immediately used, and it won't take up, or immediately stored using this scheme, and it won't take up any extra space. Okay, so the way you can design this index allocation, or this index file, is you can use a linked scheme, which is what's shown here. So so what's shown here is just index allocation, but a linked scheme, this is what happens if the index file overgrows itself. So what you can do is, or you make a very small index file, you can actually link different blocks together. So say maybe make this the overflow block. You can link this to it, and then you can continue on. So if all of these already fill up, then you can link another block to it, and you can continue. So even if you decide to make your index block really small, index file, really, really small, so that you are trying to be as space efficient as possible, you can still chain them together to accommodate large files. You can also use a multi-level index. So this is similar to the multi-level page table. So you would have level 1 of your index table, and that would index into smaller levels, and then finally to the actual block. And you can use a combined approach, and this is what's seen in Unix. So in this combined approach, the index block actually has a bunch of levels. So the first level is aimed at accommodating small files. So these are direct blocks that will map directly to blocks in your secondary storage. So these index blocks will map directly to another block. So that's just like in the very beginning, we're talking about this linked allocation just directly links to another block. And that'll accommodate small files. So then if a file grows beyond that, then we use a single indirect, which is just that multi-level. And then if it grows even larger, then we start to use double indirects. And then if it grows even larger, we can use triple indirects. So this is what Unix sets up so that it can accommodate different types of files. So now the benefit here, these don't necessarily have to be in place at the beginning. They can be added on as necessary. And so at the beginning, if you just have small files, it can just immediately do the most efficient thing as possible and link them that way. Okay, we're back. So now, I meant to make these the same. I guess I didn't make it the same. But now, next question here is to show the block allocation assuming index allocation. So we want to assume that block 11 is the index node. And our file test here is stored in these blocks in this order. What we show for this one is going to be like this. So we have our directory, we have our file, and we show where the index block is. And then we also want to show in the index block what the order is. Okay. All right, so here we go. So I'm going to draw them. I'm going to draw 12 this time. Well, 11, but. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So our file is going to be test. It's going to have index block at 11. And so 11 here, we can blow it out. And I expect you to show me this, is going to be 9, 3, 6, 2, 8, 5, 4. Okay, I ran out of space. 10, 7 in that order. And then it's super easy. You just point it to each one of those files. So what we got here? 10 or 9, 3, 6, 2, 8, 5, 4, 10, 7. Okay. So this is what I would be expecting if I told you that I'm assuming index allocation. Okay, so some performance concerns or decisions, really. When you are deciding how you want to actually do your allocation, you have to decide on a few things. So do you need sequential access? If you need sequential access and that's all you're going to be doing, then you might as well use continuous allocation. So continuous or contiguous, allocation, because that's what it's good for. And so sequential access, that's you could also use the grouping. I'm sorry, I'm jumping ahead of myself. You could also use linked allocation or indexed allocation, but it might be too much overhead. If you need direct access, you're not going to use, you could use FAT. I was going to say you're not going to use linked allocation, but you could use FAT, or you could use indexed allocation. And I'm going to also put here you could use linked. Because in general, if it was sequential access, I mean that also is good with linked as well. They're not stored sequentially, but you can step through them one at a time, so it doesn't really matter. Okay, what about the files? Are they going to be static files? Are they going to be small files? Are they going to be growing? So if they're going to be static, again, contiguous, fine. If they're going to be growing, then you definitely want to use linked or indexed. So really, in order to decide what kind of allocation method you want to use in your OS, you have to decide on what your OS is going to be used for, what files are going to look like, and so on and so forth before you make your decisions. Let me know if you have any questions. Thanks.